Welcome to the deep dive. Today we're taking a really microscopic look at the science that drives pretty much all modern manufacturing.
Metal cutting technology.
Exactly. If you've ever wondered how these perfect, cylinders or incredibly precise parts are actually made, you're about to find out. We had a listener who was really curious about the core principles.
Yeah, the physics, the geometry, all of it.
And we're diving deep into a source for this. What do we got?
We have a comprehensive engineering training guide focused specifically on turning. And turning is, it's the most common operation for creating anything cylindrical.
Okay.
So our mission here is to basically strip away all the dense jargon and just distill the essential knowledge.
Get to the core of it.
What you really need to know to remove metal with a tool and do it with, speed and accuracy.
So let's start with the absolute basics. What is turning?
It's all about generating those cylindrical and rounded shapes.
Hmm.
And it boils down to two movements happening at the same time.
Okay, two movements.
First, the part itself has to rotate. That's your spindle speed, which we call N.
Revolutions per minute, RPM. Got it.
And second, the tool has to move along the part. That's the feed, or 5 in order.
And from those two simple movements, you get what? The three main operations?
Yeah, basically you've got longitudinal turning, which is just making a diameter smaller.
Yeah.
You have facing to make the end of a part perfectly flat.
And profiling.
And profiling, that's for all the complex curves and angles.
Okay, so this is where it starts to get tricky, right? Because speed isn't just speed. If I say machine's running at 2,000 RPM, that sounds fast.
It does.
But in machining, that's not the whole story. Let's talk about the true speed. Cutting speed, or what is it, V-valors?
Right, V-valors. And it's absolutely crucial. It's the actual surface speed, usually in meters per minute, right at the point where the tool is cutting.
And why is that different from RPM?
Because it completely depends on the diameter of the part.
Oh.
So if the part gets bigger, the surface speed goes up, even if that RPM number on the machine display stays exactly the same.
So hold on. If the diameter changes mid-cut, the stress on the tool, it just changes instantly.
Instantly, yeah. Let's see some real numbers. Say your spindle speed is locked in at 2,000 RPM.
Okay.
If you're cutting a small 50 millimeter diameter, your V-dollars is about 314 meters per minute. But if you keep that exact same RPM and move out to an 80 millimeter diameter,
Speed goes up.
it jumps to 502. That's a 60% increase in speed.
Wow.
And that means a massive increase in heat and wear on your tool. This is why you have to calculate it. You need to know the true speed the tool is seeing.
That makes so much sense. So speed is all about heat and tool life. What about the actual, the geometry of the stuff we're removing? That's feed and depth of cut.
Right, 500 others.
Give us the quick definition for depth of cut.
Depth of cut is just how deep the tool digs in. We measure it as half the difference between the starting diameter and the finished diameter.
Simple enough.
It's what drives how much material you're removing.
Okay, and then you've got the angles. This feels like a really subtle detail, but I get the sense it's critical.
Oh, it's everything. The main one's the entering angle, or KPR. It's the angle between the cutting edge and the direction of the feed.
And why does that angle matter so much?
It's not just geometry, it's a force director. It determines where the load hits the insert, how the chip flows away. It's the difference between a clean finish and a part that vibrates itself to death.
Okay, so if we move from the geometry of the cut to the material itself, everything changes again.
Completely.
You can't cut aluminum the same way you cut hardened steel, right? So engineers break this down into 6 ISO material groups.
That's right. P, M, K, N, S, and H.
Let's focus on the ones that cause the biggest headaches.
Good idea.
Right.
So ISO P is steel. It's the biggest group, but its machinability is all over the place. Depends on the carbon content.
Okay.
Then you have ISO K, which is cast iron. The chips break nicely. They're short, which is great.
Yeah.
But it has these tiny abrasive particles of silicon carbide in it.
And that just grinds the tool down.
It just sandpapers the edge away. Very, very quickly.
And what about the really exotic high-performance stuff?
That's ISO S. Think heat-resistant superalloys. Titanium in Canel. They're sticky. They generate incredible heat that doesn't escape.
I've heard they work hardened. What does that mean?
It's the worst part. As you cut it, the material right under the tool instantly gets harder. So the next pass has to cut a material that's even tougher than the last one.
Oh, that's brutal for tool life.
It's extremely short.
Mm-hmm.
And then at the top of the pyramid, you have ISO H.
Hardened steel.
Pure, unrelenting hardness. We're talking 45 to 65 on the Rockwell C scale. It's just insanely abrasive. It's like trying to cut a jewel.
This brings up the question of energy. If you know the material, you need to know how much raw force it takes to cut it. There's a term for that, right?
There is. Specific cutting force,
Right.
or KC1. It measures the force needed to shear a specific area of the chip.
And I'm guessing the numbers vary a lot.
The contrast is stunning. I mean, think about the easiest material to cut, something like aluminum, an ISO-N material. Your Terrans might be around, say, 350 newtons per square millimeter. Manageable. Now, try to machine that ISO-H art in steel.
What's the number?
It's somewhere between 2,550 and 4,870.
Whoa.
It's not just a little harder. It's the difference between slicing through soft butter and trying to slice a granite countertop with that same knife.
And that force dictates everything. Your machine, your setup.
Everything. The rigidity, the power, all of it.
So we've established the goal isn't just to cut, it's to control that little ribbon of metal that comes off, the chip.
Exactly. If the chips get too long, they can wrap around everything, scratch your finish. They can even be a safety hazard. So the insert has to be designed to make sure that chip breaks.
And there are good ways and bad ways for it to break.
Oh, definitely. The ideal is self-breaking. The stress inside the material just makes the chip curl and snap off on its own.
Perfect.
If that doesn't happen, the next best is breaking against the tool. It curls back and hits the insert. The one you want to avoid at all costs is breaking against the workpiece.
Because that'll ruin the finish.
Always. It damages that brand new surface you just created.
So the little grooves and bumps on an insert, the chip breakers, they're designed to force one of those good breaks to happen.
That is their entire job.
This leads us to a big choice. Positive versus negative inserts. What's the trade-off?
It's all about strength versus cutting force. A negative insert has a strong 90-degree wedge angle. It's a tank. It can handle heavy cuts, interruptions, but it requires more force to push through the material. A positive insert has a sharper angle, less than 90 degrees.
So it slices more easily.
Much lower cutting force. It's perfect for those sticky ISO-S materials where you want to minimize heat, or for machining long, skinny parts where you can't have a lot of tool pressure causing vibration.
So you give up some edge strength for a cleaner, gentler cut.
That's the trade-off. Strength versus vibration.
How do manufacturers help you choose the right geometry for a specific cut?
They use what's called the FMR approach. It's based on the feed and depth of cut you're planning to use.
FMR.
F is for finishing. These are for light cuts, low feed rates, all about surface quality. R is for roughing. These are the workhorses. Big depth of cut, high feed rates. Just pure metal removal.
And M is for medium, the middle ground.
The general purpose choice, yeah. Covers the widest range.
Okay, let's tie this back to that entering angle, KAPR, that you mentioned earlier. How does changing that angle affect, say, a roughing operation?
It's a beautiful little bit of physics. When you reduce the entering angle, let's say from 90 degrees down to 45,
right,
you're actually making the chip thinner, even though your feed rate is the same.
How does that work?
You're spreading the load across a much longer section of the cutting edge. It means you can actually run a higher feed rate without increasing the stress on the tool.
It's like spreading your weight out on snowshoes.
That's a perfect analogy. You boost productivity and reduce wear at the same time.
Let's talk about an innovation that really plays with that FMR decision, wiper inserts.
Ah, wipers.
Yes.
They sound like they're for cleaning up, but they're actually about productivity, right? They absolutely are. A normal finishing insert has one single radius on the nose. A wiper insert has a complex shape with multiple flatter radii along the edge.
Up to 9 of them, I read.
3 to 9, yeah. And this hugely increases the contact area between the tool and the part you just cut.
So what's the bottom line for the user? Why would I want one?
You get a choice. You can double your feed rate and get the same surface finish as a standard insert, which cuts your cycle time in half.
Oh.
Or you can run at your normal feed rate and get a surface finish that's twice as good, maybe good enough to skip a grinding operation later.
So it's a direct path to saving time and money.
It is, but they demand a really stable, rigid setup because of that increased contact. No vibration allowed.
Let's shift to what a lot of people consider the biggest challenge of all, internal turning. Boring.
Yes, boring. You're basically machining inside a dark tunnel.
It's the worst-case scenario for stability, isn't it? The tool is just hanging out in space.
Completely. It's a cantilevered setup, which makes it incredibly prone to vibration. And of all the forces involved, the radial cutting force is the real villain here.
The force that pushes the tool sideways.
Exactly, away from the center of the hole.
And what happens when that force wins?
2 bad things. First, the cut depth changes. You get chatter and vibration, and the hole ends up out of tolerance, oval-shaped or bell-mouthed.
And the second thing?
The tangential force is also pushing the tool down, which can reduce your clearance angle and cause rubbing. It's a fight against physics, and every extra millimeter of overhang makes that fight exponentially harder.
So the tool itself has to be unbelievably rigid.
Precisely. The rule is always use the biggest bar diameter that will fit in the hole and keep the overhang as short as humanly possible.
But for deep holes, that's not enough.
Not even close. This is where innovation was critical. A standard steel bar might handle an overhang of 4 times its diameter. Maybe. But the breakthrough was dampened boring bars.
How do those work?
They're often reinforced with carbide, and inside them is a dampening mechanism, basically a heavy mass on springs, tuned to absorb those specific destructive radial vibrations.
It's like a shock absorber for the tool.
The very, very precise one.
And what does that let you do?
It lets you machine at extreme overhangs. We're talking up to 14 times the bar's diameter.
14 times.
It turns a job that was practically impossible into something stable and routine. It's a complete game changer for complex parts.
So we've gone from the physics of speed to the geometry of chip control and the material science of force. It's clear that every single choice, it's part of this huge decision matrix.
Everything is connected. The angle of the insert, the material of the boring bar, it all has to work together.
And for you, the listener, the real insight here is seeing that getting the best performance is always about managing these very specific, quantifiable trade-offs.
Yeah, the data in the handbook makes it so clear. It shows that depth of cut, eBay, actually has a very small effect on how long your tool lasts. And feed, Futschenneller, has less of an effect than the cutting speed, Futschenneller.
So we're left with 2 main levers we can pull, and they seem to work in opposite directions.
That's it, exactly. Cutting speed, Futschenneller, is the single biggest factor that determines your tool life. You control it to manage heat and get the most out of your inserts. But feed, Futschenneller, is the single biggest factor determining your productivity. You push that number to get the cycle time as short as possible.
So here's the final thought. If you're setting up a massive high-volume job, every second you save on the cycle time is worth thousands of dollars. But you also need your tools to last a predictable amount of time.
The ultimate balancing act.
Which factor do you push first? Do you optimize speed for tool life, or do you push the feed for a faster cycle time? That right there, that is the core economic trade-off that every single machine shop on the planet has to solve every day.